Greetings, ChemStars. This is Ms. McCauley bringing you your Chapter 3 videos. I want to remind you that while you're watching these videos, you should have the volume turned on, you shouldn't just be reading closed captioning, and you should be really actively engaged with the videos. That means pause if you need to take a minute to write down some notes, rewind it if something wasn't clear. So welcome to Chapter 3. We have Introduction to the Atom. Okay, so let's start at the very beginning. The atom, from philosophical idea to scientific theory. Here's our I can statement. I can explain the law of conservation of mass. That's one of our key vocab terms. The law of definite proportions and the law of multiple proportions. Key vocabulary will be conservation, mass, and proportions. So starting at the early models of the atom. As you learned in middle school, an atom is the smallest particle of an element that retains its identity in a chemical reaction. So it is the smallest bit of matter that you can have. The first person to coin this term was Democritus. He was an ancient Greek, and he did a thought experiment. So he didn't have any tools, he didn't have any lab equipment, but he thought about it, and he said, if I took a piece of cheese and I cut it in half, and cut that half in half, and that half in half, and half and half and half again and again, eventually I would get down to a piece that was so small that it could not be cut in half anymore. So that's where he came up with the word atoms, which was a meaning not, and tomos meaning cut. So an atom is something that is not cuttable. You can't break it down any smaller. So that's where we got the beginning of this law. Let's talk about the three laws then. We have the law of conservation of mass. This is the most important one that's going to be in this section. So what does the law of conservation of mass actually mean? It means that in a chemical reaction, mass is neither created nor destroyed. So here's an example of a picture. So if we take carbon plus oxygen, we'll get carbon monoxide. One atom plus one atom gets me one molecule, but look at what's conserved. We have a green and a red, and we get a green and a red on each side. And on the flip side of that, if we break down carbon monoxide, if we have one carbon and oxygen bonded, we're going to get one carbon and one oxygen out of it. So the same number of atoms on the left equals the same number of atoms on the right. Our next law is the law of definite proportions. It says that chemical compounds contain the same elements in exactly the same proportions by mass, regardless of the size of the compound or source of the compounds. So let's kind of break that down. What does that actually mean? So what does that actually mean? That means if you go to school and you get some water out of the drinking fountain, it'll be H2O. If you go home and get some water out of your sink, it'll be H2O. If you go down to the Ohio River and get a water sample, it will be H2O. So whenever you get water, they'll have the same elements in exactly the same proportions, regardless of where you got it from. Water is water is water. And then let's take a look at our law of multiple proportions. So what this means, if two or more different compounds are composed of the same two elements, then the ratio of the masses of the second element combined with a certain mass of the first element is always a small whole number ratio. That sounds like probably a lot of mumbo jumbo to you, but let's go back to our water example. If you have H2O, you can see that there are going to be two hydrogens for every one oxygen. You will never see something like H1.5O2.7. There'll be a small whole number ratio. So all of the chemical formulas are going to be made up using integers. Okay, let's go to the next page. So here's our example. We have three compounds and they all have potassium, remember chemical symbol K, and oxygen, symbol O. They are compared. Analysis shows that for every 1 gram of oxygen, we're going to keep that constant, the different three compounds have 1.22, 2.44, and 4.88 grams of potassium respectively. So how does this support the law of multiple proportions? Okay, so let's set up some ratios. Let's see, I'll do oxygen in blue here. So oxygen, we have 1 gram of oxygen to 1.22 grams of potassium. We have 1 gram of oxygen to 2.44 of the potassium, and we have 1 oxygen to every 4.88 grams of the potassium. Now the ones are the same, but let's look at this. 1.22, 2.44, and 4.88. Looking at those numbers, what do you see? Do you notice that I'm doubling it every time? So here I'm going times 2, here I'm going times 2. So what that really means is if we did some math here and we divided out each of these numbers by 1.22. This first example, well, that would be 1 potassium. The second example, if I took 2.44 and divided it by 1.22, I would get 2 potassium. In my third example, if I took 4.88 divided by 1.22, I would get 4 potassium. So I have 3 different compounds. They all have oxygen, but one compound has 1 potassium, 2 potassium, 4 potassium. So what could these formulas maybe be? This really illustrates our point, because maybe the symbol is something like OK. Maybe it's OK2, or maybe it's OK4. Once I've analyzed those masses, I can see that they have ratios of whole numbers. So 1 potassium, 2 potassiums, or 4 potassiums. Okay, let's move on to our next I can statement. So I can summarize the 5 essential parts of Dalton's atomic theory. So Dalton was our second atomic theorist. He was the first guy to actually do some experiments. And if you want to know more, if you go to our lesson guide for this topic and you check out these I can statements, I've linked in different YouTube videos that explain and highlight these experiments and what you need to know. So you can click here on these, and that will help you with that. So let's go to the basics of what we need to know. Okay, so Dalton, he was really into looking at gases and the weather, and he did lots of experiments, and here are 5 things that he came up with. All elements are made of indivisible particles called atoms, so everything is made up of atoms. He said atoms of the same element are identical, so if you had an example of copper maybe in the wires in your house, it's exactly the same as copper that's in some jewelry. He also said atoms of any one element are different from those of other elements. So copper is not the same thing as gold. He also said atoms of different elements can physically mix together or chemically combine in a simple whole number ratio to form compounds. Chemical reactions, our last one here, occur when atoms are separated, joined, or rearranged. So chemical reactions, separated, joined, or rearranged. Atoms of one element, however, are never changed, I want you to underline that, are never changed into atoms of another element as a result of chemical reactions. That would only be things like nuclear reactions when that happens, which we will study later. So let's try and illustrate these. So let's say maybe I had a sample of hydrogen. Hydrogen is made of hydrogen atoms. We show those with H. So if I found hydrogen in a balloon, it would be made up of hydrogen. But if I went and found hydrogen on the sun, it also would be only made up of hydrogen. So that's showing us first 2 tenets. But then let's look at number 3. Any one element are different from those of others. So is hydrogen the same thing as oxygen? No, of course not. One is something that you breathe. The other one is a super explosive gas that made the Hindenburg blow up. So how can we use that same example to show number 4? Atoms of different elements can physically mix together or can chemically combine in whole number ratios. So if I take hydrogen and I take oxygen, just like we did in the physical chemical lab when we let the little split on fire went pop, we actually were burning hydrogen and oxygen together, and we got a new compound, water, which has very different properties than the properties of an explosive gas and another pretty reactive gas. And let's see that 5th one, separated, joined, or rearranged. So if we made water in the lab, we didn't really change what the atoms were. It's still hydrogen and oxygen, now they get just combined. They didn't all of a sudden turn into gold. So you can't take water, do some alchemy, and get gold. That does not work in chemistry. So that's the summary of the 5 parts of Dalton's theory. So let's practice that. I want you to take a moment, pause the video, and I want you to try and fill in these statements. There are 5 tenets to his theory, and there are going to be 5 that you fill in here. Okay, now let's go ahead and check your work. So let's look at the first one. There is no difference between the copper found in an ancient Mayan necklace and copper wire found from freshly made copper ore. So copper is copper is copper. What could that be? Well, number 2 sounds pretty good. Atoms of the same element are identical. B. When methane, CH4, burns, it combines with oxygen in the air to form molecules of water and carbon dioxide. Well, let's see. Number 4, different elements can mix. That sounds pretty good. Chemical reactions. Number 5, separated joint. That sounds pretty good. So right now I'm thinking maybe either 4 or maybe 5. We'll come back to that one. C, the formula for ordinary ethanol and the formula for acetic acid. Okay, so C2H6O1, C2H4, those are different. Okay, so what could that be? Chemical reactions, different elements physically mixed together, simple. That seems like maybe number 4. It doesn't seem like number 1, doesn't seem like number 2, probably not number 5. Let's go on to D. We'll come back to that one. Matter can never really be thrown away. That is one reason recycling is so important. So that means we cannot destroy matter. Number 1 sounds pretty good. All elements are made up of atoms. Well, maybe, I don't know. What about number 5? Chemical reactions. Things are separated, joined, or rearranged. Never change into something else. It's always there. Maybe number 5. Let's figure that out. And then E. Zinc is a softer metal than iron and reacts more readily with acid than iron does. So that's showing that zinc is different than iron. So atoms of the same element, no. Maybe number 1 for that one. All elements are composed of tiny particles called atoms. That kind of makes sense. And I haven't maybe used that one there. So let's put this one in. Now, 4 fits best, I think, for C now that we look at our work. So ethanol, number 4, yeah, chemically combined, having different whole number ratios. Okay. So if I made C 4, let's look at 5 here. When methane burns, it combines with oxygen to form molecules of water. I think that this one really shows number 5 better. Okay. Well, look at this. Oh, I didn't use number 3. Let's go back and see which one of these actually fits number 3. The atoms of any one element are different from those of different elements. That's a better answer for E, isn't it? So don't be afraid to go back and change your work as you evaluate what letters you've used. So I think that one really illustrates 3 pretty well. So we've used 2, 3, 4, 5. That means that this one should probably be 1 then. Matter cannot be thrown away. All elements are made up of atoms. I think that's a pretty good list. So I want you to pause here and make sure you've got all your notes filled out, and we're going to pick up with our next video starting on page 3.